Excellent. Okay, let's get started. Thank you, Paolo, for a very kind introduction, and thank you to the organizers for inviting me. The topic of this workshop is very dear to me because I believe in this enterprise, and I have worked on it for some time. So, but I'm going to start by situating it in the context of some high-level philosophy, if you don't mind my doing that. So I want to start with this slide, which actually captures how I want to pursue computer vision now. I don't think this is the way we could have pursued computer vision 30 years ago, but today we can, thanks to all the development of technology we have. So this idea really goes back to Turing. So Turing in 1950, his famous paper, he had this idea that the way we can build intelligent machines is by trying to start with a child and then give it the experiences that a growing child has, and then you will have this fully developed adult intelligence. Now, this was 1950, which is quite far-reaching. Now, the difference is that between 1950 and 2020, we are 70 years later. So in these 70 years, we have had major developments in the techniques for machine learning, which we can draw on, major development in fields like computer vision, robotics, and so on. There's also been major development in psychology and neuroscience, and in particular, the understanding of how children develop. So we can actually draw on all those insights in order to embark on this program of educating Turing's baby. Okay. So the goal is, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? Okay, so here is a paper that I have picked from the child development literature, which is very appropriate to our topic. And this is from like 1985. So this is, and this is representative of a lot of work that has been done. This is about the development of sensitivity to depth information in human infants. And 3 cues are considered: kinetic, which is what in our community we would call structure from motion or optical flow; binocular, which is basically from your 2 eyes in stereopsis; and pictorial, meaning the cues which are available even in a single image. So we can see depth even in a single image, and that refers to pictorial cues. Now here is the observation. The observation is that, I mean, they do it on experiments with babies, that some sensitivity to kinetic information may be present at birth or soon after. So motion perception comes early and drives our early even grouping and depth and so forth. Next comes sensitivity to binocular information, which appears between 3 and 5 months. So between 3 and 5 months, you use your 2 eyes. You're able to fixate, make use of the disparity signal for depth. And then sensitivity to static monocular information appears between 5 and 7 months of age. So after that, we can see depth even in a single picture. These findings may direct research on the development of neural mechanisms. But these findings may also direct research on sort of some of our computer vision ideas on this, and computer vision combined with machine learning ideas. So the pictorial depth part, which is where you can see depth in a single image, it requires some supervision. So currently, a lot of the research in the computer vision community has been based on supervision from ShapeNet and so forth, and now there are better data sets available, but ShapeNet played a pioneering role. Now, I'm arguing that for the human child, there is no access to CAD models like ShapeNet, right? What the human child has access to is kinetic and binocular information. And that provides the 3D models, which then are used for supervising the training of shape from even a single image. So I believe that enterprise is useful for us in computer vision as well. So here's my statement of this philosophical goal now in computer vision terms. And this is a goal I believed in now for at least a decade. My research goal is to develop the ability to 3D-fy any image, so even a single image. And I want to 3D-fy it so I can imagine replacing each one of these objects by some kind of a 3D model so that you can move around and see what that scene would look like from different viewpoints. But the initial training has to occur if you want to make it natural, just from acquiring multiple views of an object. Now we can start solving that problem. So again, this is an area where we have worked on for some time. And in fact, two of the people who are going to be presenting after me, Anju Kanazawa and Shubham Tulsiani. So those have been at Berkeley, and we have worked together on various problems in this space. And I'm just going to show you the result of the last paper in that series. This is from Shubham Goyal, different Shubham than Shubham Tulsiani, Anju and myself. And here what we were looking at were photographs of birds. So lots of photographs of different birds. And from that, we are trying to build some kind of a generic 3D model of a bird, as well as a texture map. And then we develop the ability that even from a single image of a bird, we can 3Dify it. And in this work, we showed that we didn't even need key point knowledge to be able to do this. So this is not your traditional setup for structure from motion or stereopsis, where you have one instance and you look at it from different viewpoints. So this was a harder version of the problem in a certain sense, because the different views are of different instances. Okay, next, what I'm going to talk about today, my work today is primarily, it's unpublished work, and it's all on the theme of the more classic version of the problem, the classic version of what's sometimes called SFM, sometimes called stereopsis, which is where you have multiple views of the same instance, the same object. And what we are going to do is we call this differentiable stereopsis. So stereopsis is a very classic term. I mean, in computer vision, it's been there. People have studied it for 60 years. And differentiable refers to how we combine it with the latest ideas on differentiable rendering. So let me get into this problem statement. So the problem statement is very simple. All you're given are a bunch of views. So here are 8 different images of some 3D object. Okay. And we also, let's say, have access to their masks. So maybe you run sort of mask RCNN on this and you get segmented out from the background. And that's what this is. And we might have some noisy camera guesses. Okay. You might, for example, you might have a few points that you can match on these views. And then you can run like some standard call map or something like that to find the cameras. So that's this setup. So that's the input. And that's the input, and this is the output. The output is a dense shape. Okay, and what do I mean by dense shape? In our case, this means a mesh reconstruction. So in my group, we believe in meshes. Okay. So we've been doing this now for several years now. We regard this is like the standard representation in graphics, and the computer vision community has, of course, moved on to more newfangled things, but I'm an old-fashioned guy. I'm going to stick with meshes. If you can produce results in meshes and you have meshes and texture, you can do, you can use the standard machinery of the computer graphics community. So we have shape as a mesh, and then we have a texture map. And then we also maybe can correct the cameras, I mean, as part of this process. So now you can do anything you like, because meshes and texture is the representation that graphics people love. So that's the problem we're trying to solve. Very straightforward. Okay, and here are some results. Okay, so here are, let's say, 8 views. And we had maybe the cameras were given with some noise. So they're not ground truth cameras, but maybe they could be off by like plus minus 20 degrees. But here's the reconstruction of the 3D shape, and here's a reconstruction of the texture map. Here's another result, and this is from like a typical product images that you might get from an Amazon catalog. And what you will see here is, you get the masks from just white background kind of stuff. And sorry, I apologize. And this is the 3D reconstruction, and this is the mesh. Okay, here is a pretty classic data set for people in multi-view stereopsis. It's called tanks and temples. And here you have 15 views of this horse, and the cameras we can get from using call map as a generic SFM technique. And then this is the 3D reconstruction that we can get. So I'm starting by showing you results so that before I go into all the theory and the algorithms, you have some faith that yes, it's worth listening to this talk because they actually have some results in there. Okay, so now let's get going on. Now you know what the problem we are trying to solve is. And this is, of course, a very old problem in computer vision, right? The problem of structure from motion, multi-view. And I have picked some like papers from like in the last 20 years, but in fact, the work goes back like 50 years, okay. When I started my PhD in 1980, there were already stereo algorithms which people were developing at Stanford. Okay, now this learning from ground truth 3D is what has been very common in the last 5 years in the neural network era. So you start from something like a ShapeNet kind of model, you have some views and you try to learn the ability to 3D-fy from a single image. But the problem with this is too much supervision, and this is unnatural supervision. A child doesn't have access to CAD models. Okay, sorry. Okay, and then there is the work from our group, which has been without ground truth 3D from just multiple views, and then we like birds, and we did this work for birds, but I won't talk about it. I mean, this is work from Anju Kanazawa and Shubham Tulsiani. And I should, of course, acknowledge the big new thing on the block everybody is talking about for the last year or two. It's NERF, NERF, NERF. And I really like that work. It's from colleagues at Berkeley and Google, and it's been, the pictures are beautiful and very impactful work. Okay, what am I going to talk about? So this is the problem that setting we had. We have images, we have masks, we have noisy cameras, and we want to get at the shape and texture. So if I want to pose this in the classic computer vision terminology from 20 years ago, this would be called the problem of wide baseline stereo, because the cameras can be quite far apart. Okay, normally when you do stereo, the two cameras are very close to each other, which makes the problem much easier. But if you have views which are very far apart from different angles, it's much harder. So that's what was called the wide baseline stereo. So that's the problem. And what is challenging about it? You have one image, two images, and we have the classic idea of stereopsis. Once you have correspondence, you can compute disparity, you do triangulation, you get depth. But it's the correspondence problem which is hard, right? So what do we do? Okay. So when the views are close enough, that standard techniques work, right? So like there's photosynth and so forth. They are all based on ideas like that. So what we did here was something old and something new. The old idea here is an idea called model-based stereopsis. This is from a paper we wrote like 25 years ago. Okay, so this is presented at SIGGRAPH, Debevec, Taylor, and Malik, 1996. We had a section of that paper talks about something called model-based stereopsis. And the idea is something like this, that we are going to do this iteratively, and basically given your current guess of the shape, you will try to solve an easier correspondence problem. I mean, I'm going to go into it in a bit more detail. So that was an idea we had back then. And then, of course, what we have now are the whole machinery of differentiable rendering. Okay, so what's the idea of differentiable rendering? Well, we are going to have some loss function. Maybe it's in the rendering, in the image plane. And from that, you back propagate to changing some aspect of the shape or the texture map or whatever. And again, this is now a technology. And I mean, there's this work of a soft rasterizer from Hardy, but we can look at packages like PyTorch 3D, and they give everybody this capability. So you don't have to write your own differentiable renderer. Okay, so let me first explain the idea from like the 25 years ago. So this is like from this paper from SIGGRAPH 96. So what we are trying to do is to match what we call this key image and this offset image. Okay, and these two images are very different because the camera angles are very different. And trying your stereo algorithms at the time, which used to be taking blocks and matching them, the views would look very different, and then the disparity would get all messed up because your correspondence would be messed up. Now, our idea was that what if you have an approximate idea of the shape? So in this case, the approximate shape is a plane. So if you have an idea of that approximate idea of the shape, then with that, you can apply, take that and sort of predict the view from the new location using your current guess of the shape. So that's what we do by taking this offset image and warping it with the help of your current model. And now we have to solve the correspondence problem and estimation of disparity between these two guys. And this is an easier problem because the two are much more similar. So therefore, your usual correlation-based stereo and so forth will work much better. So at that time, our idea was just that it makes for an easier correspondence problem because wide baseline is hard. Use your current guess of shape to get to making it a problem more or less similar to narrow baseline. Okay, now what we are going to do is, so now this is 25 years later, what are we going to do? We're not going to do that kind of warping business. Essentially translates to estimating shape and cameras, right? But now we are going to do this using the tools of differentiable rendering. So let's get into that. So it's our algorithm is like super simple. I really love this approach because often when we develop new ideas, they get more and more complicated over time. This idea is actually much simpler than the kinds of approaches we used to write papers on 20, 30 years ago. I can basically explain it in like 10 minutes and this is it. I mean, what you hear in the talk, you will never need to go read the paper. This is so easy, you've got it after this talk. Okay, so there's a simple differentiable stereopsis, blah, blah, blah. Okay, essentially all you do is you have got your shape, S, pi stands for the cameras, pi for projection. So I'm going to correct them using some gradient descent step. And there's something is basically some differentiable rendering mumbo jumbo, where we are going to look at the images and from that we'll try to figure out how to correct the shape and how to correct the cameras and just repeat. That's it. Nothing more. It's super simple. Okay. There's very easy to explain because that's all there is to it. So let me get into a bit more. So here is some object for which I have different views, and this is my current shape. Okay, so what I can do is if I have a shape, then I never estimate the texture. I merely transfer the texture. So I can transfer the texture from this source view or from this source view. Now, which view should I transfer from? So note that in different views, only a part of the object is visible, right? Because if you think about this object, in one view, I might see the front side, another view, I might see the other side. So to see the entire, so that the entire texture map is not going to be visible in any one view. You might see like half of it or even less. So when we are texturing this shape, we should do it from the appropriate view. Okay. So and the appropriate view is the one where there is no occlusion and where it's most foreshortened. Okay. So that's the texture transfer that we can do. Okay. Next, we've got a target view. And with these, I can render. So now I'm going to render. Recall I have an approximate camera, right? So I am going to render from these views and given my current guess of the shape and my current guesses of the cameras, I can render what this object should look like from the view 3, right? That's what I've predicted it should look like. And this is my actual view 3. Now, these are the two between which I can have a loss. Right? I can have a loss because this should be the same. So in my old days, if you remember what I was talking about, this 25-year-old paper, at that time we would try to warp and then try to find this correlation between Windows or SSD or something. So here we have the moral equivalent of that. So there's some loss on the texture, some loss on the mask. So I get this texture loss. And now, okay, now the magic of differentiable rendering. So your backprop. So you're now getting all these losses going back. So these, the effect of losses is to compute some gradients, which then go back. So I'm changing, correcting the camera pi 3, correcting the camera pi 2, correcting the camera pi 1, and I'm correcting the shape as well. And the shape is represented for us by a mesh of vertices. And then I perturb each of the vertex of the mesh as a result of this gradient flow. So hopefully the shape gets a little bit better and the cameras get a little bit better. And that's it. You're done. You've learned the whole algorithm. You don't have to read the paper. Okay, I'll just show you some pictures and try to convince you that this actually works. So here are some 8 views, and this is the 3D reconstruction. Okay, here is another object with 8 views, and there's other 3D reconstructions. So note that these are dense reconstructions. Okay, note that the topology can be quite tricky. And in our case, we always start from this initial guess of a sphere. Okay. And if you thought we could only do 2 objects, here are lots more objects. Okay. And even more objects. And basically we've done this on, hundreds of objects. Okay. And and we can do this from 4 views, 6 views, 8 views, 12 views, and so on. Okay. So now let's get quantitative and compare with other techniques. So what are the other techniques we can have? Okay. So, call map is your generic structure from motion technique, but the basic issue with call map is that, so nice thing is that it doesn't need anything else in advance. You just run it, it'll find some sparse correspondences, and then it'll give you the cameras, and the cameras will be rough. But most importantly, the shape recovery is very sparse because you need to find corresponding points. And on smooth areas, you have no points. So call map will give you a reconstruction, but it will be a sparse point cloud. Okay. Now with NERF, we can get dense reconstruction, and with differential stereopsis, which is our technique, both of those will give us reconstructions. The basic difference is that, and we'll back this up with numbers, is that the NERF approach, with enough views and good enough cameras, it works really well. So in the regime when you have lots of views, good cameras, NERF and our approach work equally well. Okay. In the regime where you have very few views or your cameras are noisy, that's when I think NERF starts to sort of break apart. NERF really likes multiple views, whereas our approach still holds up. So that's the basic claim, that in the regime of what used to be called wide baseline stereo, I have maybe just 4 views or 6 views. Okay. And you might even have noisy cameras. Our approach sort of keeps on holding up. Okay, so let's see some more results. So call map, the main point is call map is great. I mean, structure for motion is great. It gives you cameras, but it gives you sort of sparse reconstructions, not dense point clouds. And that depends on the luck of the draw, in the sense some objects have lots of smooth surfaces, some objects have lots of texture, and depending on that, you will do well or bad, poorly. Okay, so here are some quantitative comparisons, and basically we are comparing with NERF here. So what you see here are sort of curves corresponding to the chamfer distance. So the chamfer distance smaller is better. So we have these curves, and on the x-axis is the number of views. So 4 views, 6 views, 8 views, 12 views. So all the approaches should get better as you have more views, right? When you have 4 views, they all will do less well. Okay, so that's point 1. Then we have DS, which is our approach, and then we have NERF. And this is a variation of NERF called NERF opt, where in addition to doing the usual NERF thing, you're also trying to optimize for the camera. And we have three curves here, which is R10, R20, R30. These refer to the amount of noise there is in camera. So in the camera pose. So we think of that 10 means that it's perturbed only a little bit. 20 means there is much greater noise. So it's like plus minus 20 degrees, plus minus 30 degrees. So what do you expect? So the DS curves are solid lines and the nerve curves are dashed lines. So you should compare in the same color. So this dashed line blue curve and this dashed line solid curve. So these are the comparison between nerve and DS. So these are correspond to the noisiest case, which is this 30-degree noise in the cameras. So you see that basically both approaches like to have more views. So as we get to more views, we do better. But the nerve curve is higher, which means that it has got higher error. Okay. Now, so this was with 30-degree noise. So suppose I had 20-degree noise. So then you get these other curves, and these again, these are better. Both approaches do better with less camera noise, but again, nerve is slightly worse. But the difference doesn't matter once you get to enough views. Okay, and then if you have only 10-degree noise, then they are basically can't be distinguished from 6 views on. So if you have relatively little camera noise and lots of views, no reason to pick one or the other. They are the same. It's only in our approach is, I believe, more robust. And okay, here's another measure, which is normal consistency. So that was for shape. So this was in terms of sort of surface normals. And so the measure is with taking dot product. So higher is better. And again, you see the same characteristics. So the solid lines are our technique, dashed lines is nerve. Everybody does better with more views. See, they are all getting there. So with more views and with the green curve is always is the better one, right? This is when you have less noise, and obviously your results are better. Okay, and then we can do so this approach uses both the mask, which makes you think of sort of space carving and stuff like that, and it's using that signal for sure. But it is also making use of the signal of the texture, because just to do an ablation where if you were not using the texture signal, then this would be the kind of reconstruction you would get. You would kind of get the outline of the shape, but you would not get the concavities and things like that, for which you really do need to be looking at the texture. And this is the ground truth. And here are some, I think I've already shown this picture before, more results. And so yeah, with these product images, they are interesting because basically the underlying assumption in all this texture transfer is that you have Lambertian surfaces. Because when you have specularities, then that assumption is not true. And that is what is responsible for some of the errors in these product images. But it is something which can be fixed in this paradigm, because we could, of course, do differentiable rendering with more sophisticated BRDF models, but to be sure. And here are some more results on the tanks and temples data set. And again, CallMap, I'm not trying to say CallMap is bad. CallMap does what it does. It finds the cameras and it finds sparse reconstructions. For dense reconstructions, you need to go to NERF or our technique. So more reconstructions. And I'll conclude here, and there'll be a little bit of time for questions, which is that it is a very simple paper. It's taking a pretty classical idea, implementing a differential rendering, but basically this is now a way to do reconstruction of 3D from multiple views. SFM techniques, which people have used for the last 50 years, they'll do a reasonable job on finding cameras, but not on dense point clouds. You usually have to do something on top, whereas the approach we have will give you dense from the beginning because it's recovering meshes. The two techniques you can use for recovering dense shape are our technique, differentiable stereopsis, as well as NAV. The differences are they both have differentiable rendering in them. So what's the key difference? First order difference is one is surface based, one is volume based. I mean, there are other differences like using some like this implicit this function thing, but to me the more fundamental one is surface versus volume. And for many views they'll both do well, but for few views and noisy cameras, not nosy camera but noisy camera estimates, DS is more robust. And I believe that this is a solution to the classic weight baseline stereo problem. And the paper will be on archive, and I'll end here, and I'm happy to take questions so long as we have time. And
thank you so much, Jitendra, for the presentation and also the great timing. So I see already a couple of questions. One is from Andrea Vidaldi. He's asking, what are the limitations of meshes and when do we need to switch to something else?
So this is a philosophical debate. So I think there are no limitations of meshes. They are a pain to deal with, but there are no limitations. I mean, so that's a extreme statement. And the limitations are, I mean, the problem, what makes them difficult to work with is this problem of topology, right? So in our scheme, we start from a sphere, and these objects eventually are not just of the sphere topology. So what we have to do is we keep reconstructing, and at some stage we go to a point cloud, we remesh. We go to a point cloud again and remesh, and those stages, and then you use marching cubes from the point cloud to mesh. So once the point cloud is sufficiently good, then the meshing will give you the right topology. So this aspect is a bit painful. I think that this is where the approaches of using an implicit function, I think, are nice. They are elegant. They don't have this mess. So I can appreciate that. I think that the nice part about meshes is it's standard infrastructure in graphics. So I mean, we don't have to reinvent any new wheels. We just plug into their pipeline. And I mean, we can do this for maybe I'm just sounding like a conservative old guy. I'm saying I want to just adopt the legacy stuff there is, and I like meshes, and that's it.
Actually, I had something connected to that because I was wondering how you handled the change of topology, but you indeed answered to that. Maybe I can, before pointing some other to some other questions, I wanted to ask something connected to this. So, of course, going back in the old days, then there were also the other methods that had a different approach to deal with the change of the topologies, like level set methods, where basically they have this implicit volumetric representations. And what do you think? Is that maybe too heavy at this point to use for the resolutions we want, or?
No, that's a good point, but I think the level set methods are essentially what are. I mean, I always, when I talk to the people using NERF and so forth, and the implicit function methods, I tell them, hey, have you gone and read those 1990s papers? Because the implicit function, the level sets are exactly that, right? That's exactly the same idea. Yes. I mean, that was the same insight which was there in 1990s in the work of people like Jamie Sethian and so forth, right? Which
and Osher.
And Stan Osher, yeah. So the answer is it's exactly it's the same insight. It's a good insight. Okay, it's just implemented in a different way in the neural network formalism. So I feel that yes, people are onto this. So yeah, I think that since we went down this mesh path, we have to deal with this problem in a more messy and inelegant way.
Okay, and maybe one last question, although we're at the limit. Maybe what are the limitations of CalMap, and whether we need to switch to something else?
CalMap is the result of a lot of the work on it. I mean, it is your classic SFM, and CalMap does it is an optimized result of 50 years of computer vision and maybe photogrammetry for 200 years. So Colmap is great. I think Colmap doesn't give you dense reconstructions. And I want dense reconstructions. I just don't want a sparse point cloud. So that's so Colmap does what it's supposed to do. I think I want more than what your classic SFM does, because classic SFM gives you a point cloud and the points are determined by where you have texture. On a smooth flat wall, that's not where classic SFM is supposed to work. Its formulation is different. So I'm not blaming that. I'm going to answer just one question, which is from, I think, Friedrich Karl, which is it fair to compare to NERF, which is optimized to produce photorealistic images, not 3D shape? Yeah, I mean, that's the one I have to compare to somebody. I mean, so what we did was we said NERF, agreed, their original goal was images, but implicitly they do compute shape. And I think that there's a whole industry around NERF now, and there are lots of papers which focus on the shape that is extracted out from NERF. So that's why we thought that it's a fair technique to compare to, because over the next year, you will see NERF for everything, right? So I think that's why we are just getting ahead of the curve. And we actually considered a version of NERF which is optimized in terms of cameras as well. So yeah, so that's the answer. Then someone else is asking about details. Yeah, I think that part has to do with having fancier losses. Maybe we can tweak that a bit and do better. Yeah, I think I answered all the. Have you tried the algorithm training without mask supervision? Answer is it doesn't work well without mask supervision. So I think that the question is whether how well will it work with noisy masks, as you might get from a just a regular mask RCN. And then we have some results which show we can do it, but I would not claim that, okay, we have solved that problem fully. In the first paper in any approach, it is good to keep the approach as simple and unadorned as possible. And that's what we have done. I've explained the entire algorithm to you, and it takes 2 lines. So we can always add engineering improvements, but I prefer not to do that in any of my first papers. People need to appreciate the idea before all the engineering gets thrown on top.
Okay, thanks a lot, Jitendra, for the presentation, all the answering the questions.